Alright, now it's time for Dr. White's fun with graphs, and this time we're going to talk about matchings of bipartite graphs specifically. And so we're going to go over what the definition of a matching and how to find the largest possible matching in a graph. So a matching is a subset of edges such that for any distinct edges in the matching, they do not intersect. And so we're only going to work with bipartite graphs. The idea is you got this bipartition, and you're looking for a set of the red edges. So a set of edges connecting each vertex in one set to a vertex in the other, and such that you don't have two red edges intersecting. So the second graph is not a matching because these two red edges share an endpoint. And so usually this is discussed in the context of marriage, men and women, trying to marry them off. Other real-world applications involve job applications. These are a set of positions, these are a set of applicants. Can you ensure that every job gets filled? Who cares if there ends up being someone unemployed? You just care that every job actually gets filled. Or another application is these are the set of homework problems. These are the group members. The group members each attempted certain problems. Can you guarantee that each group member makes exactly one contribution to the assignment? And usually the goal in graph theory is to find the biggest matching you can. So on the way to defining how to find the maximum matching in a graph, we have to talk about alternating paths. And the definition of the alternating path is that it's a sequence of vertices starting in A, so you fix one of the sets in your bipartition, it's A, and every other edge is in the matching. So it's a path in the graph where every other edge is in the matching. That's why it's called alternating, because if you color the matched edges with a different color, you see that the colors alternate on the path. So black, red, black, red. And to find the maximum matching, it turns out you're going to be looking for certain types of alternating paths. So for instance, suppose someone gives you this graph, and they ask you to find the maximum matching, and this is the matching they found so far. Well, you notice that currently there's three edges in the matching, and the question is, can you do better? Well, if you notice, starting from 1, vertex in A, you can create the alternating path 1A, 2B, 2B3, C4D. And this is called an augmenting path. And what makes it an augmenting path is that both the first vertex, 1, and the last vertex, D, are unmatched. And the fact that they're unmatched and the fact that the path is alternating tells you, in fact, that the path involves an even number of vertices, and therefore an odd number of edges, because every other edge has to be red, and you must be ending with a black edge and starting with a black edge. Moreover, the number of black edges has to be greater than the number of red edges by exactly 1. So, as we see in this graph, you have 4 black edges and 3 red edges. And so what that means is that if you switch along the path, meaning you change the colors, you swap which edges are in the matching so that the black edges on the augmenting path are in the matching and the red edges are not, you now have a new matching that's bigger by exactly 1 edge. And every algorithm for finding maximum bipartite matchings actually uses this idea. If you go through the graph, you try to find augmenting paths, and you keep going till you can't anymore. Alright, so here's the procedure for finding a maximum matching. First, you start with no edges in your matching, and then you continue to repeat the following steps. You find an augmenting path in your bipartite graph, and then you swap along the path. And as we saw, whenever you do that, you increase the number of edges in the matching by exactly 1, and you keep doing this until there's no more augmenting paths. And so let's try that with this example. Suppose that these are 5 different jobs and that these are 5 different applicants, and they decided that these were the only applicants qualified for these positions and that they're all equally qualified. Can you actually fill every position? Well, let's try the algorithm. You can actually start with any vertex you want. Let's pick A because A only got 1 applicant, so clearly that person has to be the one for the job. So let's add this edge to the matching. Please note, of course, that that is an augmenting path. If you have an edge between 2 unmatched vertices, that is also considered an augmenting path because it's alternating and it ends on 2 unmatched vertices. It's kind of a trivial example, but that way the algorithm starts. Now let's just play randomly and just do this algorithm. Let's look at vertex 1. Let's just go ahead and be greedy and say that vertex 1 goes to job B. All right then, now let's look at person number 3. And well, the person number 3 can't get job B because it's already in use, so let's assign him to temporarily to job number D. All right then, and now let's look at person 4. Person 4 did in fact apply to job C, so let's go ahead and add that. So far we have a matching with 4 edges, and of course the question is, can we do better? Well, let's look at person 5. He only applied to job D. And so let's see if we can find an augmenting path. Well, if we go 5D, 3B1, we get an alternating path, but it ends on a matched vertex. So that's not augmenting. We want augmenting paths. So that doesn't work. If you go 5 to D to 1, then you have to go to B and then down to 3, and yeah, we keep finding only alternating paths. It doesn't look like an augmenting path exists. This looks like it's the best matching we're going to get. And this isn't the only matching for this graph, but it looks like the largest matching is size 4. And of course that might be counterintuitive because we had 5 jobs and 5 applicants, so you would expect it to be possible to fill every job, but our algorithm only gives us 4. And in the next video, we'll actually prove that you can't fill all 5 jobs, that this is the best we can do. Now here I'm going to attempt the algorithm again with a different set of choices. This is to actually illustrate augmenting paths at work. Sometimes they don't pop up, but sometimes they do. So suppose that we've already matched 2 with A and 3 with D because we were picking them arbitrarily. And now we look at, say, 5. And now we try to find an alternating path. Well, there's an alternating path from 5 to D to 3 to B. So we see that that is an alternating path. More importantly, both 5 and B are unmatched. And so we actually do have an augmenting path. It's not just alternating, it's augmenting. So let's do a swap. So now after some messing with the art program, I managed to do a swap. You now see that 5 and D are matched and 3 and B are matched because those were the black edges of my augmenting path. And now I've increased the size of the matching. And now I can either try to match 1 or 4. If I try 1, I see I run into the same problem. Both the vertices 1 is attached to are matched. And so I guess one could try to find an augmenting path. But if you try, you will quickly see that there are no augmenting paths with 1, so let's go to 4. And 4 is adjacent to C, which is unmatched. And so again, we can match 4 with C, and here we see a different maximum matching with 4 edges. And so picking a different starting point, we got an entirely different matching, but we didn't end up getting a bigger one. And so it seems that the maximum matching is size 4. If you're wondering what makes this algorithm work, it's a theorem due to Burge that if you have a graph and any matching inside of it, that matching is the biggest possible matching if and only if there is no augmenting path, which is a alternating path, so every other edge is in your matching, and the 2 endpoints aren't matched yet. Note that this doesn't guarantee it's the only matching of maximum size, just that there's nothing bigger. Of course, we don't discuss matchings for general graphs much in this course because it turns out actually running this algorithm that I described for general graphs can actually cause problems. So those who are interested might look up Edmonds Blossom algorithm online, and that gives you a algorithm and procedure to find a matching, the maximum possible matching in a general graph. But the one I described here works for bipartite.